Okay, ladies and gentlemen, then I think we can start. This is the last session today after a very interesting day. I think we had a lot of insights on different topics, and it's a huge honor for me to chair this session due to the fact that we right now, after a lot of theoretical input, we also get a more practical insight, and therefore I'm very happy to welcome our three speakers, Mrs. Hinton, Mr. Müllner, and Mr. Kärkinen. I hope that is rightly pronounced. We first would start with Ms. Hinton. Ms. Charlene Hinton is a senior consultant for cybersecurity at EY. Within the Pioneer program, she completed a Master of Science in Public Sector Innovation and E-Governance at the Public Management Institute at the KU Leuven. And today she will speak about the state of ethical AI in practice, the case of the Estonian public administration. I think that is very interesting. For many years in the European discourse, we hear that the public administration in Estonia is way ahead when it comes to digitization and let's say smart governance. So I'm very happy to give you over the floor. Ms. Hinton, the stage is yours.
Thank you. We'll start sharing my screen and let me know when you see it. All right. Well, good afternoon, everyone. My name is Charlene, as was introduced, and I'm very delighted to be presenting to you my research on the state of ethical AI in practice. This research was conducted as part of the master's program, the Erasmus Mundus Public Sector Innovation and E-Governance, from which I graduated just this past September. Over the next 15 minutes, I will walk you through my research by providing some context on AI ethics in the public sector and explaining how I use the value-sensitive design as a framework to come up with the results and later on open a discussion with the audience. So without further ado, let's dive right in. A number of research and reports have shown that AI has vast potential to change the way we live in society. And along with these benefits, there are risks that are associated with the AI, particularly as it relates to the loss of autonomy and decision-making and the unintentional bias that may arise from algorithmic systems. Now, there have been discussions as well around the ethics of AI, not only in academia, but in civil society. Given the lack of regulation of the technology and process surrounding this technology, which the European Commission is quickly changing with the introduction of the AI proposal this April. However, most governments have limited understanding of the implications of the use of AI, and there has been a lack of empirical research, context-based AI use in governments, and how this can lead to systemic failures. So despite the prolific introduction of AI ethical frameworks, the research and application of AI ethics in the public sector has been inadequate. So against this backdrop, I pose the main question of my research. How do public service organizations ensure ethically aligned AI? And what are the key issues that they face in the design and development, as well as what are the ethical principles that may have been considered in practice during the design and development of these AI solutions? In order to answer these questions, I use the value-sensitive design as a framework of inquiry to parse through the state of ethics in practice. Now, the VSD is a social technical framework designed by Friedman et al. In the early 2000s, and it places human values at the center of technology development. VSD has a characteristically tripartite methodology, as you can see on the screen: conceptual, empirical, and technical. And these three components allows you to inquire about the values that are considered in the design. The stakeholders, both direct and indirect, may be implicated by the technology, as well as the technological mechanisms that allow these values to either thrive or in some cases be suppressed by them. But because the framework doesn't have a prescribed set list of ethical principles, I complemented this framework with the AI for People's ethical principles. These principles are recognized in another very practical field of application, which is biomedicine. And these principles have been distilled from a number of leading references on AI ethics. So with these two frameworks combined, it provided the basis for my methodology. Now let's head over to Estonia, one of the most digitalized societies in the world. Estonia has over 90% of its government services digitalized and available online. I had the privilege of experiencing this while I lived there for over a year. And although this time of year it's quite frigid as the temperatures plunge into the negatives, Estonia also has been proactively building its AI competence and has launched a national strategy as early as 2019 or 2018. And now the government has seen over 70 different use cases of AI throughout. I interviewed 8 agencies and I applied the VSD to 7 of their 70 AI use cases. Now, these use cases ranged from my diverse set of public service domains that covered finance, public infrastructure, public safety, regulatory oversight, and even social welfare services. Because I sought to understand how these AI solutions were being designed and developed, there were also diversity in the types of AI applications that were being built. There were chatbots, decision support tools that helped with voice transcriptions, some risk assessment, facial recognition, forecasting and planning, and heavy machine learning to be able to deliver on these functions. I also interviewed agency personnel directly involved in the AI design and development. And I analyzed their responses through thematic coding. Now, there are a number of limitations with this methodology, but I'll mention the most important one being that this approach did not allow for values to naturally emerge because I used a much more structured set list, which is the AI for People ethical principle. So as a result, there was some open to loose interpretation of the responses and which values they related during the analysis. So with this caveat in mind, let's go over to results. The first key theme may be surprising when placed in the discussion of AI ethical principles, but it's really important not to overlook the challenges that government agencies faced. When I first asked about ethical implications across my interviewees, I was met with responses along the lines of, we are not really concerned about that right now because our solutions are not so developed or advanced to be thinking about societal and ethical impact. Primarily, the agencies face the challenges with data. In one of the respondents' mind, he shared that there isn't really an agency that he knows of in Estonia that is seeking to violate human rights intentionally. And the focus really, he believes, should be on problems where they exist right now. And more specifically, he's referring to problems with data and the performance of the AI. And that was expected to bring efficiency, but through their feasibility studies and prototyping, they're still struggling a little bit with that. So even though Estonia's advanced when it comes to digitalization, they're still trying to get into the details and iron out a lot of their challenges when it comes to data. For example, some agencies sat on years and even decades of data, which should be an asset, but because of certain regulations in place, they could not access this data for the purposes that they would like to now. Similarly, there were agencies with poor data quality, which required massive amounts of effort to prepare for training of the AI, and they do not have the manpower or the knowledge to be able to do so. There were also cases where data was just not enough or sufficiently available. For example, one agency wanted to transcribe phone calls, which were mostly in Estonian. And in Estonia, there's only about 1.3 million people who speak the language, potentially, unlike a larger language pool of English or Russian or Mandarin, where these things are readily available and could be easily used to be fed into the AI algorithms. Because of this, it would also mean it would cost more for them to develop and further train their AI. And as a result, the performances of these prototypes were not so promising initially, but they are still committed to working through and developing the AI to the full operational use. A lot of the agencies also contracted an AI vendor to help them through the development. And because AI is such a new technology for agencies, even the process of procurement became a challenge because they just don't know what is enough or what to look for in these vendors. So again, like to reiterate, the main challenge for them right now is related to data and AI skills. The second result that was uncovered is an extension of the first. There is an awareness of AI and ethical frameworks by the designers, but again, the focus more is on feasibility and not so much on ethical implications. Here on this slide, I laid out the 5 ethical principles from AI for People and tried to map them to what was observed based on the responses. Across all agencies, the most cited value for developing AI was the promise of efficiency in serving citizens or the benefit of the citizens or beneficence. When it comes to non-maleficence, the principle or the key ways this was demonstrated was through privacy, security, and safety measures already in place, mostly as a result of compliance with regulatory expectations like the GDPR. In terms of autonomy, almost all use cases did not have an autonomous decision-making element. So for them, this already throws out the concern for any kind of failed decision-making that was made by the system itself, because the ultimate decision still resided with the humans. And outputs are often reviewed because there is an awareness of the fact that their solutions are not that advanced to be, or not fine-tuned yet to provide accurate outputs. So they've already still put in place a mitigating factor, which are the humans. When it comes to justice, interestingly enough, indirect stakeholders were not considered or involved in the early stages of development. They did not involve citizens, for example, who will be implicated by the use of their solutions. And in some cases, even though they are already using some of these prototypes, the citizens were not informed that they were using such a thing. The primary reason being was that their solutions are not so advanced and that there's still that human element that barricades for any potential wrongdoing. And that's why they didn't feel the need to inform the citizens. But when asked in the future, should citizens be aware or be made aware of such a thing, almost all across the board, public servants shared the principle that transparency is a must. Yes, so in conclusion, I was able to answer the research question in that, yes, AI ethical principles are indirectly considered and somewhat practically demonstrated, but these are not necessarily put into practice rigorously or systematically due to more pressing issues related to data, skills, and overall immaturity of AI for now. So based on these results, I've come up with some practical considerations for designers, for governments, and even for AI vendors. So the first being that AI designers should actively consider these ethical implications early on in the design phase, which the VSD framework emphasizes. And it also advocates for indirect stakeholder involvement throughout the development phase. From a government perspective, government should provide resources to increase AI uptake and skills in the public service, or in public servants, just as Estonia has or is currently doing. They have a lot of different knowledge sharing workshops to help public servants learn a little bit more about AI and how they can best share practices for implementing their AI use cases. And for third-party AI vendors, they are in such a strong position to increase awareness and actual implementation of ethics as they help guide agencies in the development and the design development of AI. So I would like to finish my presentation, and I would like to thank you for your time and attention. I can then open up for questions, any kind of discussions, if we have time available.
Thank you very much, Charlene. We definitely have time. If there are any questions, please feel free to ask them. And if there are not directly questions, the thing that I was wondering about, how do you think would your findings, are they translatable to other countries? How do you, or to which extent do you think that these findings are a specific Estonian case?
When it comes to generalizability and application to other countries, obviously the main consideration would be the level of maturity. And if they are in the same boat as Estonia when it comes to the maturity of their solutions, I heard in Kosovo, they're also facing similar concerns, similar challenges related to data, and that ethics becomes more of an afterthought. So with the rate at which AI is being developed, it could be said that this could be applicable to them as well. I think through this research, primarily, it's important to understand that AI is not that advanced yet, but that this research brings to light what's currently happening and that academia and policymakers should take heed.
Thank you. We have another question from Elisa, please.
Hello.
Oh, now it's working. Thank you. Yeah, thank you very much for this great, interesting and revealing presentation. And yeah, for me, it's not surprising that when AI is in its very early phase that yeah, ethical concerns are rather put behind. So we firstly think about feasibility and all the stuff you just presented. And yeah, as you said, that's definitely a problem and we should work on that. Did you already do some research on how we can overcome these challenges? Because that's also something I'm working on in my everyday work life. And it's actually not so easy because, of course, the designers and all the AI experts are embedded in the business context, so they have to deliver feasible AI systems and probably not invest so much time into the ethical concerns. Did you also reflect on that, or somehow is that somehow related or integrated in your work as well?
Yeah, so actually that part would be the next step of any future research on this. It wasn't covered in my research, but the kind of work I'm doing right now at EY here in Amsterdam relates to more, well, how can we raise awareness amongst our clients? Like, how can we embed this kind of ethical by design early on, as opposed to more reactive once a possible potential regulation on this comes into play. So unfortunately, I don't have further details on that. I haven't done the research, but I do think that regulation will play an important factor in arm wrestling organizations to comply. Otherwise, that's the soft law or ethics. It's really more on the onus is on organizations to follow. And if there isn't strong incentive to do that, it will remain the back burner. I wish I had more of a concrete answer for you.
It's a big project, I would say. So I'm looking forward to the next results. Thank you very much.
Thank you. Thank you.
Yeah, thank you very much for those questions. Is there another question from the audience? If no, then thank you very much again, Charlene, for your presentation. And it is an honor for me to present our next guest, Peter Möhner. He's a PhD student and researcher in the social computing team at the Know-How Center of the Technical University of Graz. So we get input from Austria. The title of his research project is The Impact of Meta-Learning from Privacy-Preserving Recommender Systems. Peter, the stage is yours.
Okay, so hello, thank you very much for the nice introduction. Yeah, I'm Peter, and I'm going to talk a little bit about, in the next few minutes, about the impact of meta-learning for privacy-preserving recommender systems. And this presentation is partially based on joint work with Elisabeth Lex and Dominique Kowald. Okay, so I'm pretty sure you all know some large-scale recommender systems out there. For example, we have Spotify in the music domain, we have Netflix in the movie domain, and we have, of course, also Amazon. What all those large-scale recommender systems do have in common is they don't generate this one-size-fits-all recommendations. They don't just, for example, recommend the most popular item to all of its users, right? So what they do instead is they personalize. They fine-tune their recommendations to the specific and fine-grained needs of each individual user, of course, in order to increase the accuracy of recommendations. However, this personalization leads to the necessity to include more and more user data. For example, a user's interaction data, or even a user's personal data like age, gender, occupation, things like that. This large or enormous utilization of very large amounts of user data, of course, leads also to some issues regarding the user privacy. Very sensitive attributes of the user could get leaked by the recommender system, either via a data breach on the service provider side or via inference attacks. And also, quite noteworthy, also state-of-the-art methods could potentially, under some circumstances, leak very precious user data. And this work is based on some prior work of us, which is called Robustness of Meta Matrix Factorization Against Strict Privacy Constraints. And here we acknowledge the fact that users have different inclinations to reveal information about themselves to the recommender system. So there are users that reveal more data about themselves to the recommender system, and there are users that do not want to share their data with the recommender system due to privacy concerns. The reason behind it is, in my opinion, clear. There can be no data disclosure if there is no data, if the users don't share the data with the recommender system. And in that sense, each user has his own privacy budget, which is just the fraction of data a user reveals to the recommender system. And just for a more precise explanation, we say that if a user has a very small privacy budget, the user has high privacy, but bad recommendations, because the user shares just a tiny fraction of data with the recommender system. If the user has a large privacy budget, the user has low privacy, but will get very good recommendations because the user shares all of its data with the recommender system. And this is, I think, quite obviously a very important trade-off between accuracy and privacy. And the question here is, can we have both? How can we have high privacy, but also high accuracy? And one concept we were interested in, or we tested if this would make this accuracy privacy trade-off easier, is meta-learning. Why? Because meta-learning has been used for problems related to privacy. For example, the cold start problem in the recommender systems domain, or also few-shot learning. And in one sentence explained, meta-learning, or with meta-learning, you learn a model for a group of users instead of learning a model for each user individually. And yeah, for the experiments or the results I'm trying to present to you during the next few minutes, we used a very recent approach by Lin et al. Called Meta Matrix Factorization, or MetaMF, which is a recommendation model, matrix factorization plus meta-learning. And yeah, we use MetaMF to basically just underline the impact of meta-learning on privacy-preserving recommender systems. And therefore, I'm going to present to you some side-by-side comparisons between MetaMF with meta-learning and the variants developed by us, which we call no MetaMF. That's just MetaMF without meta-learning. And I also tried to structure the results in the next few slides based on 2 research questions. What is the benefit of meta-learning for small privacy budgets? That's the first one. And the second one, do small privacy budgets impact users differently? Let's get started with the first research question. What's the benefit of meta-learning? Yeah, let's just explain those 2 plots first, maybe. On the left-hand side, we have MetaMF with meta-learning, and on the right-hand side, we have no MetaMF without meta-learning. On the x-axis, we have our privacy budget beta, which is just the fraction of the data a user shares with the recommender system. And on the y-axis, we have our relative accuracy loss metric, which is just the loss of recommendation accuracy under privacy budget beta relative to the accuracy loss of a model without any privacy constraints imposed on it. And here on these 2 plots, we already can make some very interesting observations, I think. For example, here we can see that for a privacy budget above 0.5, there is no substantial increase in the relative accuracy loss. So the recommendation quality does not get worse. Users get similarly good recommendations, even if they only share approximately 50% of the data with the recommender system. The second observation is that if we decrease the privacy budget further, somewhere below 0.5, the accuracy loss metric starts to increase, which means that the user or that the accuracy of the user recommendations get worse. The users get poorer recommendations if they share less than 50% of their data. That was our MetaMF model with meta-learning. And now let's look at this picture without meta-learning, no MetaMF. Here we can observe, in general, similar things. If the privacy budget is above 0.5, there's not a tremendous increase in recommendation accuracy. If the privacy budget is below 0.5, the recommendation accuracy starts to decrease. However, the point here is that the increase in our relative accuracy loss metric is far more severe with our no MetaMF model than with the MF model. Sorry. So with that, we can say that meta-learning really helps to keep the recommendation quality high, even if users share just a tiny fraction of the data with the recommender system in order to sustain their privacy. So here we can see that the benefit of meta-learning is, in one sentence explained, that we can have high privacy and also higher accuracy than without meta-learning. Then in the second research question, we analyzed the effect of meta-learning on different user types. And here I just picked one specific data set, the Duban data set, obviously just for space reasons. And in a typical recommender system, you have different kinds of users. For example, you have high involved users that really frequently and often interact with the recommender system. You have medium involved users and you have low involved users that only occasionally interact with the recommender system. What we did here was we identified these 3 user types based on the number of ratings and then tested our MetaMF and no MetaMF model specifically on these 3 user types, or we evaluated the performance of the recommendations on our low, medium, and high user types. Yeah, and just focus here not on the. I mean, of course, we can make similar observations than before, that the accuracy stays the same if you have a privacy budget above 0.5, accuracy drops if you have a privacy budget below 0.5. But most interestingly are, in my opinion, the differences between the different user types. Here, for example, for our model with meta-learning, and for the low-involved user type, the recommendation accuracy stays actually the same, even if they share just, let's say, 20% of the data with the recommender system, for example. So those low-involved users are really robust against small privacy budgets with meta-learning. In contrast, if we look at these high-involved users, these power users in a recommender system, the relative accuracy loss metric increases quite strongly, which would indicate that their recommendations, that the quality of their recommendations drops substantially. On the right-hand side, we can see again that there is no real increase in the relative accuracy loss measurement for the low-involved users, but for the high-involved users, the recommendation loss actually explodes quite strongly. So they are really severely impacted by small privacy budgets if we use no meta-learning. So with that, we can say that, and this is maybe I would say maybe the second key observation of this presentation, the second key takeaway, that that meta-learning really severely impacts these high-involved users. Okay, let's slowly come to the conclusion, and I also would like to take a few seconds to talk about our future work. Yeah, we've seen that if users reveal more than approximately 50% of the data to the recommender system, recommendation quality stays the same. Accuracy only marginally decreases. If users share less than 50% of the data with the recommender system, this is the case where meta-learning is required in order to sustain a higher level of accuracy than without meta-learning. We've seen that low-involved users can afford privacy. They're pretty robust against small privacy budgets. However, in contrast, high-involved users have to sacrifice a lot of accuracy for privacy. Their recommendations get far poorer if we don't use any meta-learning. So this means that we have very individual and personal accuracy privacy trade-offs among our user population. Yes, to our future work, we aim to cover 3 points in our future work. The first one, we want to consider that there is data with different sensitivities, and I'm sure we all can relate to this. There is data points which you would be comfortable with disclosing, and there is data which you would like to stay in private. We want to incorporate this in our research. And the second point is that we want to decide what data should be shared based on data characteristics to sustain accuracy. It is a well-known fact that accuracy of recommendations is correlated with certain properties of the data set, and with this we just want to guide or help the user to decide what data the user should share in order to increase recommendation accuracy, but be able to share less data. And third, we want to work on the following point. Not revealing data could impact the recommendations of other users. So in a typical recommender system, my data is used to generate your recommendations. So if I do not share my data with the recommender system, there is the possibility that this will also impact your recommendations. And for this specific question, I'd like to refer to a recent paper of us, which is a position paper in which we propose or present a conceptual approach for privacy-aware simulations, because this recommender system simulations serve as some sort of laboratory to investigate exactly these very complicated and complex questions. Okay, so thank you very much, and I'm happy to answer any questions if there are any. Thanks.
Thank you very much. And I directly hand this over to you. Are there any questions from the audience? No, I don't see any questions. Thank you very much, Peter. It's a very interesting work, I think, that you're doing there. And as the time is going further, I'd like to give the word to our third presentation today. Mr. Kärkinen. He's the chief AI expert in Huawei Public Affairs and Communication Department. It's very nice to have you here. You were a member of the high-level expert group on AI of the European Union that provided the AI ethical guidelines that we all know and the recommendations on trustworthy AI to the Commission. He has a long career in industry, research and development and academia, and he has a PhD on theoretical physics from the University of Helsinki. So we're happy to have you here. The stage is yours.
Thank you. Now I guess I have my voice as well here. So let me just put the kind of a screen on the slideshow. Thank you for the presentation, so I don't have to present myself. I will just go to certain statements in the way that actually starts the claim. I think that defining artificial intelligence is very hard, but certain things we know. Intelligence is complex, and so artificial intelligence has to be complex as well. We also know that computers are really stupid. And then we know that in order to have artificial intelligence, we have to factorize the complex systems to some simpler rules. So now there is this epistemological questions about the thing that do we think that all intelligence or all complex systems can be factorized to multitude of simple rules? And this is what essentially happens in artificial intelligence. And if that cannot happen, if there are some emergent properties that are actually coming out of, let's say, that cannot be reduced to simple rules, then AI will never work for those. So this is the question about how complex and how complicated systems are related to each other. So
excuse me when I interrupt you for a second, Mr. Kärkinen. Unfortunately, we can't see your screen yet.
You can see the screen. Okay,
the screen sharing hasn't worked, no?
So let me see that if I would share a screen now. Let's try again. So do we see anything now?
Yes, your desktop, not the presentation.
Yes, my desktop. And then what I will do next is to find out a way to share my screen. Now what do you see?
Yeah, that's the wrong screen.
That's the wrong screen. And let's see that if I can change the screen. There is a place around here which is saying that remote control about
exactly on the screen that you're sharing. There is the setting. There are display settings, and if you click on that, then usually you can switch. Yes, it's on the left. On the left.
One, yeah. On the left when it comes up.
Up on the left, yes.
Yeah. Now it is. You say left.
Yes, on the left, close to show taskbar and slideshow.
So this one.
They're the display settings.
I should know how to use a computer, though. Let's say, is this the one? No, this is not the one.
On the black screen, exactly, with your mouse a bit above. Yeah, this could also work, maybe. Exactly, that is perfect. Yes. No, that one was the wrong. No, above, display settings above. Yes, exactly, there, and then probably exactly this one is the right one. Yes, the first one should be right. Perfect. Now it's working.
Oh, thank you for your instructions. Now I'm breathing again. Let me go through this one. So I would actually show you an example about how to create a kind of knowledge from data, and this is from open from DeepMind. And if you can look at this system, is essentially predicting where is rain is coming, and it is doing it better than we can do with physics. So it's essentially solving Navier-Stokes equation better than we can solve them currently. The fun part about this is that we don't know how to build a program that is so accurate on data. So it is doing something that is creating a closure of the turbulence model. And if you are interested, there are some links around here to how that is happening. But this is just to say that sometimes from data you can gather insights to deep learning that one cannot find in other means of physicality. So it's also a tool for explaining physics for us. not only trying to figure out what AI is and trying to explain that one. So these are the equations that are actually controlling the system from Navier-Stokes. So then there's always the thing that is called the reality gap, and it is kind of a difference between what you have in the system that you are and what system you actually are trying to describe with the data. And there is now a way of doing that to a certain extent in trying to gather, making a simulation which is called, using something which is called domain randomization. So it is such find the real physical parameters of the robot hand that is here. So what is happening is that you make hundreds, kind of tens of thousands of simulations with different kind of parameters for the robot hand. And when you do that, you actually create a system that works on all over those. So this is like saying that we have different ethnicities and our system is not working for everybody in the world. So what we do, that we randomize our system to very, very many different types of persons. And then when we run the system, we train it for everybody. So that would actually be not be kind of discriminating at all in kind of a sense. And this is not discriminating any robot that it is using. And it is closing the reality gap in the sense that when you actually then utilize the program on a real system, it works automatically. So it's able to generalize over the different kind of models of the digital twins or digital ensemble it is having. And that has helped it to generalize also to physical systems, even if the solution is not really what they are solving here. It's not really kind of a state-of-the-art physical model of the robot hand. It has some types of the things, but it is enough to train the system. So this is related to what things is that we have to have a meaningful data representation, and that is also coming to the question for the previous talk that was very interesting on systems, is that when you use deep learning on systems, you have to have a computable data representation. That is essentially a very simple one. And this is what it is in deep learning. It's just dividing the data sets to multiple parts. And this is essentially what is saying that if you look at every single line around here in the image, so the only thing that the machine learning systems or the deep learning systems can know how many yellow things they are above and below the line. So it is really privacy preserving. It's like asking about how many people, how many females live on the northern side of the city and how many males live on the northern side of the city. And it is totally aggregated data that is coming in. But when you start adding lines, there are now 12 lines around here. Sometimes you have little boxes that are coming out of it. You can see some of the little triangles that are creating. Sometimes there's only one point on those positions. And then you actually can differentiate a certain person out of the data set and it becomes non-privacy preserving. Of course, the obvious solution very often is that you increase the data set in such a way that you would have multiple points in that vision circle. Or then you can figure out other constraints for the lines, for the positions of the lines that would be say that let's not build these little triangles. Let's make it kind of privacy preserving in a way when you train it. So this is the thing that computer can do. So this is a simple operation, but now how to make these explanations meaningful for humans. So there is the second layer of what is. These are the decision boundaries that are on the hidden layer, and they are already actually describing the data in a sense that we think that are to a certain extent meaningful. Of course, you can also see that there are explanations here that are non-meaningful because there are lines in the yellow area that are going off the kind of the topic in way, and they have no really meaning on themselves. So now building explicable AI actually would require that you do something which is called concept whitening. So making it so that these features that are coming on the kind of hidden layers in the system when it is doing the classification would be meaningful for human eye. Here are only one couple of the features are actually really saying that where is the green kind of, let's say, dot and where is the red dot, and that defines the position to a certain extent. But of course, the deep learning can combine these features to actually to a very nice solution that actually describes and does the classification very easily. So this is the basic structure how everything happens. Of course, when you have images, for example, in your data or something like that, the number of lines is in millions, and also the number of dimensions is in millions, and I only have 2 dimensions here. I show this because you can see how it actually works, and then how it practically does. You cannot not actually go there and make these images in such a way that you would right away see what is happening around in the system. So then there is the kind of a way of figuring out how to find out the essential features that are defined in the system. This is kind of for my research, and it is done by Janne Huttunen and me and Mikko Honkala and Harri Lindholm. And this is essentially from health cases. So it's about deep learning, predicting cardiac indices for photoplethysmographic waveforms. So figuring out if you measure, for example, the heartbeat from the wrist or from the carotid arteries that are here in the close to the neck, you can try to figure out what can you assess from those items that you have here. So what we do is essentially follow the idea that we want to do a causal inference in our system. Let me say that I want to change the slide. Now I'm just admitting people in. So what we do here is that we think that we can use simulations to create data sets, and as we can see from the domain randomization, sometimes it works in a way. And how we try to make a model that is very diverse. So we built this kind of, let's say, over 50 different kind of arteries, and we change the lengths of those arteries in a way to produce a representative step of all populations that are coming in, young and old, and from different places, different kind of, let's say, sizes of bodies. We have also veins in the system, and then we use Navier-Stokes equations in order to, in one dimension, to simulate the system. This is actually a known model that they are based on the system that we are utilizing here, and it actually takes quite a lot of computer time to figure out how to do these 9,000 different persons that are differently setting. But we think that we train it for all of these kind of even alien populations. I would say that if they would be non-humans or whatsoever, they would still be included in the training and figuring out what can we infer for those data when we have it. And this is now purely based on physics, so it's causal, so nothing outside physical realm is coming in. The only question is that do we have the correct equations or not? And if we wouldn't have a correct equation that wouldn't fit the reality, we could actually see when we do experiments on the systems. So this is the type of a kind of a data that we can get. For example, can we measure blood pressure? And this is now the true blood pressure that is coming from the simulation, because we have done the simulation, we know that, and this is how deep learning can be used to predict it. Or we are actually using different kind of methods of using 5 features that are essentially very known features, or 21 known features that people are using for blood prediction, and then we use essentially a convolutional neural network to figure it out. The convolutional neural network gives the better result than everything, but for blood pressure, we can see that the human-generated features are pretty good to actually predicting all the blood pressure. And you can see here the error differences that are coming from. This is diastolic and this is systolic blood pressure in figuring out. But what it is means that we can actually measure and estimate the blood pressure from the kind of artery, from the arteries of the hand, for example, to a certain kind of a precision that is already good for some wellness purposes, for example, in those devices. And then if you do something a little more difficult, it is about measuring Qmax. That is about the size of how much blood is coming out of the heart. And it has always been a problem to how to measure the kind of really the capability of the heart, because that is related to your heart disease in a way. And there have been no good ways of doing that before. So you can see that some of the criteria that are using the F5 and F25, the 5 features or 25 features of the curve, has not been kind of they don't work very nicely. But if you use the kind of CNN out of it, actually predict quite nicely the kind of the Qmax on it. So this is something that usually one has not been able to optimize or measure anyway. But now we know that in principle, if the blood is kind of following the proper Navier-Stokes equations, if we put it in, it is a measurable quantity. And then, of course, the question comes from explicability. So how do you then actually get measured it? And we're using this kind of an idea about adversarial learning, which is doing 2 things in a way. It tries to find out the feature that is making the greatest havoc to your estimation. It maximizes that, and then it is minimizing what would do the best classification ever. And you continue that when you train the system, and it actually finds out these, let's say, these good features. It makes the system more robust, not perhaps more accurate than anything else, because you lose something accuracy, but you gain kind of explicability, as we have been discussing already before. And here you can see the error bars that's coming with the different systems. But when you do this adversarial training, then what is kind of coming out of the system is this kind of extremely small changes. You can see that of course, when you're talking about Qmax, then it is kind of what is the force of the heart, and you can really see it in the first kind of let's say first kind of milliseconds after the kind of heart has made its pumping feature. There is a certain little difference here that is actually depending on the heart rate that you have in the system. Two features that are coming out. These are really adversarial features in the setting. Excuse me. Setting in the way that they are very small, and I wouldn't think that the doctor would actually be able to use these features in their hand if they would see that. This is a standard way that you have a feature, but it is almost invisible in the data that you have. But when you know what the feature is, you can also build systems like microscopes that are really looking at that single feature out of it, and it is expanding. It's like a microscope which is seeing that this is the feature that I want to see. This is how I extrapolate in the way that it comes out in the data. And you could actually start making measurement systems that would measure Qmax in the system. So this is the story about how to build systems in a way that would be fair in a way, because we have a population that is extremely large, extremely diverse, because we have used this kind of balanced data sets that have constraints, essentially the types of different kind of a blood cell to blood veins that people usually have, and covers all of that variation. It is also explainable to the extent that we know what feature is important, and we could also make systems that are not based in deep learning anymore, but would actually be based on exactly seeing those features in the stream, and then classifying the system accordingly. So this is the kind of, I would say, the state of the art in figuring out how some systems can be built in a way that they results, even if it's something that using unknown ways. So people will not be able to measure this kind of a property before, and how to make it so that it becomes a practical tool. So what did we learn? We learned that adversarial robustness creates interpretability and explicability to the system. We kind of showed that not based our systems on real data but simulations ensures that there is a causality in the resulting model. So we really know that this is based on physics that is coming on. It is not a measurement mistake. We have looked at the domain randomization ensures lack of bias in the varied features, because we can produce a lot of data even for let's say the minority cases that would be happening. And if you are kind of want to kind of look at how this adversarial kind of robustness kind of is working, there is a very nice and easily kind of understandable talk by Shipani Sandukar from the website. So thank you, and I think that I have always used my time in the way, and then there would be a good place to have some questions if you have.
Yeah, thank you very much. There are still some minutes left, so are there any questions from the audience? So if you have a question, you just you can just raise your hand, and then I can unmute you directly. No, I don't see any questions there.
Yeah, so it is very understandable. It's the last talk.
No, we have a question. Please, Mr. Medina, go ahead.
Hello, Mr. Kainen. Nice to meet you. I have one question regarding this, because I mean we have gone deep into the details, but there is actually, in the last 2 years, a big discussion about explainability, and that should be actually being a start from the beginning of the design. And there is already based on the different technologies that is being used, like if they use neural network or if you use trees, that might be like explainability might be higher than on the other stages of the other technologies. Do you think it makes sense to give the possibility to companies to measure the level of explainability to start to create an awareness on that? Because of course you are knowledgeable about this area, but let's say on the implementation side, people are starting, or on the user side, they have no knowledge about this. And I think awareness is one of the most important things when we are talking about these areas. And what do you think about that? If that makes sense to offer this possibility?
So I'm kind of for something which is called meaningful explanation. So I don't think that actually showing the kind of workings of a neural network gives value for usual people who would be actually kind of subject to something. I would say that the meaningful explanation is about that you actually disclose the decision boundary. So if, for example, in the case that you are asking for a loan, and in that kind of situations, you would say that you did not get the loan because you didn't earn enough money. That was the decision boundary. And if you would have earned more, then you could actually get the loan. So this is the meaningful explanation for people that are saying it. Sometimes the providers of the AI solutions say that they don't want to disclose the decision boundaries because they are trade secrets or something like that. But I think that if the solution is something that the AI solution is something that impacts the people, then definitely this kind of explanations about where are what the decision was based on is essentially the thing that is important. And whether what kind of algorithm is behind the decision kind of a boundary doesn't really matter in a way, because this is already giving the fundamental reason why this decision was like it was.
So in that case, you're more into the point. We have the discussion in another chats today in the forum, where you are more towards to explain to the decision maker what let's say the information is coming from in terms of what are they. Let's say
here what I was saying was the thinking that I would try to make for, if you look at the AI Act, for example, then there is a role of users and then there's a role of providers. So I was explaining here what the user has to understand about the system in order to be able to classify it and understand the system problem. So what are the decisions point in the form of the pulse that would actually what I'm saying what the condition is. So this is important for the doctor, but perhaps it is not important for the person who are doing the diagnosis too. You could of course say that here you can see the peak, and this is the thing that is possible the problem that I see on the one. So it has to be tuned according to the value. If you really would think that everything that AI is doing should always be simple, we would never be going to address complex problems. So the question is that we want to solve complex problems with AI. Now the question is that what would be the simple, appropriate explanation for the system? And of course, what the AI Act is saying about it is saying that the user has to understand what are the limits of the capabilities of the AI solution that we have and how to use it. So it doesn't actually require that you understand how it works. But these are really the kind of cases how this is important to notice in how you actually in practice do it. But there is a different kind of if you go to different domains like in justice. This is, I was not talking health now, but if you go to justice domain, then there is this kind of a ruling of saying that you cannot judge people in such a way that they would not understand the legislation. So there is a separate requirement for explicability in terms of good governance. And that good governance is for public policies. And it actually requires that you have to say about what are the laws that I was using in order to do that decision that I had. And this is what humans have to do also. If they do a decision in courts, they say that according to this and this law, this was the decision that was done. And so it is actually saying that for law cases or justice cases, that the system is much more demanding than it would be, for example, cases in healthcare, where it is about diagnosis and it is not about kind of ruling of the law. So there are some differences, and it is like EU Act is actually very much use case dependent. It's really saying that you don't have to explain anything about the low risk system. There is no explicability requirements for that. It's only for high-risk systems. And these are really use case related. For example, if you are judging somebody's kind of admission to a school or a university, you have to be able to kind of do it in a proper way. That is kind of assessed with conformity assessment in that. So this would be my long answer to your question. That's it. Or do I go in a wrong direction? Is there something that?
No, exactly what I was expecting to hear. That basically yeah, it's really user case related. It is also application related and also like user related or decision maker in that case, doctor or whomever is behind. And yeah,
and it is a multidimensional matrix, and you really have to be sensitive. This requires this kind of, let's say, street knowledge in order to how to explain things to people when it happens. This is very often when you actually need human kind of involvement. It's not the case that you can actually trust kind of a gold AI to be able to do that part.
Okay, thank you very much.
Yeah, thank you very much for the question. We still have 2 questions left. On right now, no, one of the questions left. Oh no. Okay, let's first start with Rita. Please go ahead. Yeah, you can unmute yourself.
Thank you. Sorry, I can also turn on my video. Actually, it's also a follow-up to the answer you just gave, because I'm wondering if I do agree that it's actually use case related, but if I'm looking at medical systems, there's obviously also difference in those, right? So I don't think you could say that in any instance where only the doctor needs to know how the system works, the patient shouldn't be interested, because if I'm like being diagnosed on the basis of a data set or on a recommending or technology system that is based on a data set which is, I don't know, only trained on specific groups of patients, like I don't know if a woman is treated on based off a recommendation which or often AI recommendation which was only trained on male bodies, I would say that there should be an explainability requirement also in the relationship between the patient and the doctor.
I think that they should be this. Yes, you are exactly right in the say. Thank you for asking the question. So there is a particular aspect of medical decisions that are actually also kind of is a question in medication. Yeah. Now, medication they are very often analyzed by clinical trials. And very often the kind of a biochemical part of how the medication is affecting human is not known. And one never knows, and even if you would know it, and some cases you do, the chemical pathway is so complicated that there's no sense of starting explaining it. And perhaps the doctor knows it. Very often it is only a few scientists that are actually knowing, can go enough to biochemistry to figure out how life is working. Life is actually a very kind of so then I would say that no, you cannot ask in medical domain that you would have explanation for everything. But what you have had, you have to have a knowledge about what are the processes that were the clinical trials that were used. And your questions about whether something works for men or whether something works for women, they are done also for drugs. So you have to actually figure also out that, and you can do it. And this has to be done for the AI solutions as well. So these are the ones, in order to provide something like that, you have to actually go through these clinical trials. So having proper test sets that are actually going all of these variants through, and you do it in a proper way. And we were talking about the difficulty of getting data, but it's also medical kind of a drug developers have exactly the same problem. How you find people who actually are willing to take some drugs and see whether they are still alive after taking in the way. And this is of course the saying, this is the hardest, and they are very strong kind of ethical requirements, how you do bioethical systems, how you get promises of how to actually do these experiments. And these are also related to how you get the data for making. Doing medical research very often, even in AI, requires quite a long kind of approval process of an ethical judgment about whether your system is sound. Sometimes it takes 2 years.
For good reasons, I think. Thank you.
I hope that this answered your question. But indeed, it is very domain specific. So this is also very domain specific to healthcare.
So thank you very much for this question. We have a last question, Mr. Goldberg. Please go ahead.
Yes, hi, thank you. My question is actually, you started to touch on it in your response to the first question from Manuel. And I was curious if there was more to elaborate on how this approach could be used in non-medical contexts as well, since having an explicability or an explainability method or even solution that doesn't focus just on correlation, like say SHAP values and principal approaches up to now have tend to focus more on correlation rather than causation. But if we could actually have a model of explanation or explication that focused on causation, which is really what we want when we're asking for an explanation, that would be quite innovative and from an ethical perspective, quite a step forward. So just curious if you can elaborate on other contexts like AI in policing, in the defense sector, in education, if you think that this could be your approach could be applied to the non-medical sectors as well.
Yes, it can be applied to non-medical sectors, but there is this kind of, let's say, limits in understanding in the way that what you have to do is you have to be able to simulate it, because that creates the causal relation. And very often I would say that in building robotics, which are interacting with humans, one of the basic kind of rule is that you have to build a model how humans are behaving for the robot, because otherwise it cannot handle the interaction in a proper way. And also you have to kind of build a kind of model for the robot, how it has to behave in order that humans would understand how it would behave. So there's lots of this kind of a human behavior modeling that is needed, but then we are really kind of on the borders of whether there would be a simulation model that would actually give you a causal system. You would of course try to explain something that some of the cases are explained. For example, how rush hours are forming in people when they are driving the streets. We understand the behavior because there's an equation that seems how people tend to behave. And that could be causally explained how people end up in a straight road. They end up in being in a stall, or in a German terms, or in a Russian kind of in terms. So this is much harder. But there are other cases. For example, we have used for a model where we are figuring out how to measure the amount of water in the soil. So making it so that what you do it in the setting, you have some kind of a noise creating devices that are or let's say ammunitions that are making a seismic wave, and then it goes through the soil and then it reflects back. But it's very hard to figure out from that data that what is actually happening. But what one can do is the same kind of domain randomization and figuring out how different kind of soils would actually give the response and vary that randomly in a way that creates a big enough data set for variation of a soil, and find out from the back propagating signal that is coming to the sensors what is the amount of whether they could tell the amount of water in the soil the same way as we were actually looking at humans. So, but this is a physical application in the setting, and it is depending on it. But you are asking quite a lot that we could make this kind of let's say, psychological models of people that would be causations and accurate and describe people. But in those policing cases, for example, I would say that we have to use some other methods to find out what are the reasons on the kind of on the decisions, and we have to use other. And as I say, that justice is one of those areas where we have to be very careful. And they are also, even if we do a good AI system in justice domain that would, for example, do this retention problem, solve it to a certain extent, then having people involved of making the decision can make it biased again. Sometimes it is that it goes in the full system then because people they aren't like people, so you cannot actually ask more from people than and what they kind of are in the setting. So sometimes that happens. Things are complicated in some domains, and some domains we can solve. So this is a problem that we can solve for those domains where we can do simulation, depending on how much we trust in the simulation.
Perfect. Thank you. Thank you very much also for that answer. And as there are no other questions left, I would like to thank you three for your interesting presentations, and I hope that everybody else enjoyed the presentation as much as I did. And so nothing is left for me than wishing you all a wonderful good evening, and I hope to see you again in the next coming days.